At the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by different live elements. This presentation is followed by a live panel discussion where experts in the field recapitulate and debate on related ideas, questions, and open problems.
Welcome. Thank you to everyone for joining this panel session. Since we have a large panel, it was recommended that I be the moderator, so I'll do my best to serve in this role. To briefly recap, in my presentation, I talked about very large wind turbines, and I focused on a team project where we are designing two-bladed, downwind, very lightweight, highly flexible rotors. And we call this concept the segmented ultralight morphing rotor, or SUMR for short. And we've been designing SUMR wind turbines at the 13 megawatt level, the 25 megawatt and 50 megawatt levels. And we've also done a smaller scaled SUMR demonstrator, or SUMR-D design, that we're now experimentally field testing at the US National Renewable Energy Laboratory, or NREL. So all the work on this team is the result of a rather large team effort. We have about 20 team members that join our regular bi-weekly team teleconference meetings. And I'm lucky enough to have 11 of the team members join me here on this panel. I'd like to introduce all the panelists. On the team, while we do all work relatively closely together, we have roughly divided ourselves into sub-teams. So we have an aerodynamics team, a structures team, a controls team, and a field testing team. So I'll introduce the panelists by the team that they're on. We have Dr. Gavin Ananda. And so panelists, if you can raise your hand so the audience members can more easily identify you. So Dr. Gavin Ananda is our one representative from our aerodynamics team. We have several members from the structures team on the panel. We have Dr. Todd Griffith, who is a professor at the University of Texas at Dallas. We also have Mayank Chetan and Alejandra Escalera. And Alejandra and Mayank are both PhD students at the University of Texas at Dallas. So they're on the structures team. We have also several members from the controls team on the panel. We have Dr. Rohir Blom, who is a senior principal engineer at GE Research. We have Dr. Katie Johnson, who is a professor at the Colorado School of Mines. And we have Mandar Fadness, who is a PhD student at the University of Colorado Boulder. And we also have Dr. Chris Bay, who is an alumnus of the University of Colorado Boulder. So they're all on the controls team. And we also have several members from the field testing team. We have Lee J. Fingersh, who is an alumnus of the University of Colorado Boulder. We have Nick Johnson, who is alumnus of the Colorado School of Mines. And we also have Dr. Rick Damiani, who is a consultant, and he is also with the Colorado School of Mines. All right, so we all work together on this team, and I often wonder about, your opinions on different things, but sometimes I don't get to ask, so I felt like this is my chance here. So I hope to ask all of you at least one question. And my first question is directed at Rohir. So in my presentation, I talked about levelized cost of energy, and that's one of the drivers for going to larger and larger wind turbines. Rohir, being at GE, can you expound on this further? What are the business drivers for larger and larger wind turbines, and what do you see as the future for these huge wind turbines?
Yes, of course, Lucy, and thank you for that question. In your presentation, Lucy, you already mentioned that bigger and taller turbines allow to increase the power capture and take advantage of higher wind speeds at higher altitudes. And that has been one of the main driving forces behind growing wind turbines over the past decades. But for offshore installations, there are even more considerations why we would like to go big. And to understand that, let's actually go back to how we measure the cost of electricity, like you explained. The levelized cost of energy metric calculates that ratio between the lifetime cost of a power plant and the total energy production. And for wind farms, this lifetime cost include both the upfront cost to install a wind farm, or what we call the capex, as well as the cost throughout the life of the farm to operate it, the OPEX. For offshore installations, both these cost components are very strongly dependent on the number of turbines that are needed to create a wind farm with the desired output. And that's easily understood because for every turbine that we install, we incur costs at the installation and we incur costs to maintain it. I mean, lower number of units during installation means lower cost for installing the turbine, lower cost for the foundation, for the support structure, lower costs because of the specialized vessels and manpower that is needed to install those turbines. Also lower costs for the infrastructure to connect the wind turbines to the mainline grid. And similarly, during operation, less units means a lower cost of servicing and maintaining a farm, which again translates to vessel cost and manpower to access those turbines. So this is the main reason why for offshore, we like to get a rating and annual power production as high as possible. And so that's why we see also from an industry perspective, a strong driver to get to bigger and bigger wind turbines.
Great. Thank you for explaining that further. That's really helpful. My next question is for Todd. I only mentioned a few of the issues with these large wind turbines in my presentation. And Todd, I'm wondering, from your perspective as a structural dynamics expert, what do you see as the major technological challenges for these extreme scale wind turbines?
Thank you, Lucy. So this is it's a very interesting question, and I can talk about from the structural design point of view, and maybe first as some background. Our overall design objective is to produce a design that's lightweight and cost effective, but also feasible, safe, manufacturable. And the way that we achieve a design that's feasible and that works is to follow design standards, and we look at a number of failure modes, and there are a number including deflection, tower strike, strength calculations, fatigue, even aeroelastic stability or flutter. And in a more traditional design, several decades ago, you could get a workable design by perhaps satisfying ultimate strength requirements, and then everything else would work. And certainly there were a lot of challenges back then as well. But now in these extreme scale designs, we're pushing the limits on every single one of those failure modes. And it makes it extremely challenging structural design challenge. A couple of new ones that are particularly challenging for extreme scale rotors are fatigue under gravitational loading, just due to the sheer size and increase of the blades. And then also aeroelastic stability or flutter. We're really pushing the margins on performance there as well. And what's really key in terms of solving this is the team that you see here and all working together in terms of aerodynamics and controls and bringing new technologies that can mitigate these issues. And so that's a summary of what, really at a high level, the structural design challenges we face. But certainly every time that we think we've reached the limit, we thought a decade ago that a 100-meter blade was a pretty crazy idea, but we're seeing that limit has been pushed by the industry. And in this project, we're looking at 150 and beyond 200-meter blades.
Great, thank you for your perspective on that. All right, maybe similar questions for the control systems experts. I only touched upon a few of the control issues in my presentation. So for the control system experts here, what do you see as the main challenges for control system designers for these huge wind turbines? So here, maybe let's go with Katie first.
Thanks, Lucy. This is such a really exciting area to work on as a control systems engineer. So I'm really hoping that all of our audience is inspired as well. Tons of interesting control challenges. I'll just mention a couple, and then I know some of the other team will mention a few others as well. Just the sheer physical scale of a turbine like this lends itself to a number of control challenges. Even though we need that scale in order to take advantage of the higher wind speeds, as Rohir mentioned, and we've got a great structures team, as Todd described, to help us to have some good structure for the turbine. We still have a lot of physical flexibility at that scale, which makes it difficult to actuate to do what we want it to with the limited number of actuators available on a typical wind turbine. We also have at those scales really highly varying turbulence in the wind at the spatial scales that we're looking at. And so, for the wind turbine case, this is of course our energy input. So we have to respond. We can't just completely reject our disturbances. But we do have to treat from a control systems perspective these as oftentimes unknown disturbances that we address. So I'll stop there and let some of the other teammates answer some additional points.
Great, thanks, Katie. Chris, do you have additional thoughts you want to add here?
Yeah, thanks Lucy, and thanks Katie for covering those. I think for me, and Todd alluded to this, just the fact of designing a system this large, when you're designing a control system, any small adjustment or change has, significant impacts to the other systems, the other design teams. And when you're pushing the design envelope of a system like this, you really have to work hand in hand in an iterative fashion, not that traditional linear sense where controls comes in at the end to ensure performance or something like that. But, we can design a controller to minimize loading or achieve a certain, power production. But as soon as we do that, they may provide a new opportunity for the structures team, the aerodynamics team to refine their design and improve the performance even more. And so I think kind of changing the way we think about how we design controls in systems like this into more of a co-design fashion is really a big challenge. Additionally, as Katie mentioned, the size of the system for a controls engineer, you can do all the simulations and modeling that you want, but it's always great when you can actually test the system out in person. And finding equipment to do that for this size is obviously a difficult thing. Our solution was a scaled demonstrator, but I think this will be a ongoing problem for control system engineers as we try to work towards these larger and larger wind turbines.
Great, thanks, Chris. Mandar, how about you? What do you think are the major control challenges?
Yeah, so as Chris and Katie mentioned, meeting those design constraints based off of aerodynamics and structures teams for such large flexible blades has been a challenge for me. So we always have to make sure that we are getting the main goal, which is maximizing the annualized energy production. But also then due to the large flexible blades, we also have to make sure that we are operating at the aerodynamic design operating point, while keeping the structural loads low. So during the design process, we have been coming across instabilities in the blades, flap-wise and edge-wise bending loads at higher wind speeds, and also we have to worry about tower clearance and coning angles. So there are a lot of challenges and a lot of design parameters that we have to worry about while keeping the levelized cost of energy low. And as Chris mentioned, the best way to achieve this is a co-design process where the controller is tuned for every design, and we share our results with the aerodynamics and structures teams so that they can look at those results and they can get insights from them and come up with better designs to which we can tune a better controller. And I think that's the best way to get the most optimized design.
Great. Thank you all. I think you brought up a number of points, and I'm glad you are able to explain some of these better than I did in the presentation. So thank you. All right, now I have a question for the PhD students. So I'm curious, how has been your experience working on such a large team project? What do you see as the pros or the cons? Would you recommend new PhD students to join such a large team project? And what advice would you give them as to help them approach such a project? So here, maybe let's start with you, Alejandra.
Thanks, Dr. Powell. So I think it's definitely a great experience to be part of these large team. You really learn a lot by working with people from so many different areas of expertise, and I think you get maybe a better or even bigger view of the problem that you're trying to solve. So I think it's great in that sense. I would say one challenge could be communication. You have to try and get the points of view of everybody in the team heard, and you want to make sure that everybody is in the same page. So keeping things organized and keeping a schedule is very important. But overall, I've liked it a lot, and I would definitely recommend it. And maybe other PhDs here can also give their point of view.
Great, thanks, Alejandra. Mayank, what are your thoughts here?
Yeah, I do agree with Alejandra. And just to add on to what she said, one of the major things was, in addition to the field of field of research we are doing, we see the impacts on the other teams. Like in my example, we see when I'm doing research on structures, I see the impact on the controls design or the aerodynamic design, and also the feedback from the control design into the structural design itself. So that gives a good high-level perspective in addition to the deep diving research we do in our fields. In terms of cons, I would say working with a large team across time zones does take its toll in terms of communication, but I would say that our team has done a great job in documenting everything and passing on communications between each iteration of the turbine design and multiple tasks which have been involved in this team.
Great, thank you. And Mandar, how about you?
Yeah, so far I've been loving working for this project, and it's a very large and dynamic team that you get to work with. That I think is a really positive aspect of this project. And the thing is that you are, as a control systems engineer, I also get to understand the issues that aerodynamics and structures teams face, and I also get how to incorporate control design changes to address those issues. The other aspect is that this project is more of a involved project where you have to always be presenting your results with the rest of the team, and always like there are lots and lots of meetings with different sub teams with the overall team. So that can get a bit hectic. It's not like maybe a conventional PhD project where you get to sit in your cubicle and just work on your project for a long time. You always have to be presenting your results. But I think for a project of this scale, that is the best approach, and those meetings are often very productive. So yeah, I would definitely recommend new students to join this kind of project.
Wonderful. Thank you all for your comments. I just want to point out, I guess, to the general audience that both Alejandra and Mandar have worked on this project 1 year or less, and they're doing really well. They work very well together and with the larger team. As a large team, even before the pandemic, we had already been meeting regularly in teleconference, online meetings. We did very much enjoy our at least annual in-person team meeting, and we missed that, and we're hoping we'll be able to resume that in the not too distant future. All right, my next question is for the non-controls panelists. So what recommendations do you have for the controls community in working with experts in other disciplines? And here, maybe Rick, why don't you start?
Yes, thanks, Lucy. As a non-controls person and aerostructural engineer, my perspective is, and it's been touched upon before by others, is really to be on a common basis among the various teams. The controls folks really need to understand what the goals, the direct goals of the design team might be. Yes, we are after a minimum LCOE, but that's a very difficult target to achieve without going through sub-steps, I would say. So understanding really what we're after, say, in terms of deflections or loads on the various components, masses and mass schedules, bills of materials, and then, of course, performance. Those are the constraints and the ranges that we can work on, and we can try and optimize our designs with. So understanding how that control system can really impact our optimization in that sense is a key challenge, as well as is the modeling of these systems. And again, the bigger and the more flexible they become, the more we're pushing the limits of the models. So how do we go about accounting for those aspects? That's a challenge for both the controls teams as well as the aerostructural team as well. And on the other hand, the aerostructural folks, just like me, we need to understand what the limitations and capabilities and needs of both sensing and actuation might be, and how we can realize the maximum potential of the control system within our design capabilities as well.
Great, thank you. Gavin, what are your thoughts? What are your recommendations to the controls community? I think you're muted.
Sorry about that. Thanks a lot, Lucy. I think I echo quite a lot about what everyone has said. I think in general, it's really valuable for teams to cross-pollinate with each other. I found that the best work between the aero controls and structures team came about during our 1 week sprint sessions, where all the team worked really closely together. And I got to run controls codes. The controls team got to run aero codes, and the structures team got to also play around with these different types of codes, just to better understand like what are the key drivers that get at each of these performance variables. And given that it was, we're pushing the boundaries of the design space, you can't have a black box simulation that covers every situation, because that black box only is based on what is previously been historically done versus what you're trying to push towards. And so that really came about by really understanding what each team was working on, how that pushed that boundary, and then trying to punt that over to the controls team and the structures team. So in general, I think like in a much more integrated team, like really helps solve that problem.
Great, Gavin. And when you're referring to the 1 week sprint meetings, you're referring to our annual in-person team meeting, right?
Yep.
I do think that, yeah, in some ways, those in-person team meetings are very effective for bringing the whole group together. I think we've definitely been able to do a lot with the online teleconferencing meetings, but I think there's some things that are more effective when we can all be in the same room, working side by side, asking questions. And, yeah, so we all miss that. All right, so before we run out of time, I do want to have Lee J and Nick also have a chance to give their perspectives. And so here I want to ask about the field testing. You know, in my presentation, I alluded to many challenges that we had to overcome before we were able to achieve operational field testing. And Lee J, I want to thank you for all your efforts and work on the field testing. I guess, in your opinion, maybe what are the top 2 challenges that you saw in overcoming in getting to operational field testing, and what might you say is the main benefit of field testing?
Thanks, Lucy. Yeah, I think the top 2 challenges in field testing really come down to getting the controller to work on the real turbine versus in simulation. To address why that is a problem is a lot of times the simulations don't include a degree of freedom or several degrees of freedom that do exist in the real world that weren't accounted for in the controls design. And also that the simulations don't account many times for sensor problems or actuator problems, spikiness, drift, quantization noise, this kind of thing. And so in my years of testing, we've always found that the controllers usually needed some modifications in order to work in the field between when they were designed in a simulation and when you actually put them on the real hardware. And the second most challenging thing is just getting the test equipment to function in a difficult environmental system. This year, for example, for this test, we had a lightning event where we had 3,000 strikes within 45 minutes within 10 miles of the turbine. That sort of thing can cause problems. We had a lot of icing events that caused problems with some of our instrumentation. And that sort of thing is always a challenge when doing a field test.
Great, thank you. Nick, do you want to add to that?
Yeah, one of the biggest benefits that I'm seeing with the testing is that it really helps with the modeling and also with the model development. So I kind of like the old adage that all models are wrong, but some models are more useful. So I think the field testing gives us insights to the actual system and also helps us to make our models as useful as possible. Yeah, we do this by obviously comparing the actual field data to the data we're getting from our models. Yeah, and also just want to touch on some of the other things that have been talked about with the Gravo aeroelastic scaling, which has been really neat. It's allowed us to not only get insights at the scale that we're testing, but also at much larger scales. So that's kind of a part of this testing that's been done. Yeah, and it's also been really neat to be able to work with the rest of the SOAR team and kind of, yeah, work out some of the kinks with our models. And we're already starting to see with the testing data and understand where some of the limitations are in our actual aeroelastic models that we're using.
Great, thank you. And thank you all. I want to thank you all for, first and foremost, being just remarkable team members on this project. It's really been a lot of fun to work with everyone. And I also want to thank you for being on this panel. I know many had to get up at very early hours here in the US, so I really appreciate your efforts and being here. I also want to thank the Ifac organizers again for giving us this opportunity. I guess maybe just to summarize from what I heard, there is a business case for very, very large wind turbines. There are many challenges, but with that business case, that gives us incentive and a lot of opportunities to try to meet these challenges. I also heard kind of a theme that I've heard in other plenary talks, like Jing Soon's talk and other plenaries, where working on large interdisciplinary teams is really a lot of fun, and we really learn a lot about that overall system that we won't have if we just stayed in our controls silo or our particular disciplinary silos. And we definitely learn a lot from field testing. And that also, some of your comments there reminded me of Ben Reck's plenary talk on Monday, where he was mentioning that the original prediction of when self-driving cars, self-driving taxis would be available would be this year, 2020, but they're not readily available yet. And he said the reason for that is because things in the real world never match the simulation environment that we tested things in. And that's exactly what we've seen in our field testing. And so the field testing gives us a lot of data to learn from and to better understand these complex rotors. And we hope to take that understanding and develop future better rotors for better wind turbines in the future. Okay, so I want to also thank all the audience members for joining this session. And I hope everybody stays healthy and that we can all see each other again in person pretty soon. So thanks.